From HanselMinutes.com, it's Hansel Minutes, a weekly discussion with web developer and technologist Scott Hanselman. This is Lawrence Ryan announcing show number 337, recorded live Thursday, September 13th, 2012. This episode is brought to you by Telerik, offering the best in developer tools and support. Online at telerik.com. And by Franklins.net, training developers to work smarter. And now offering Gesture Pack, a powerful gesture recording and recognition system for Microsoft Connect for Windows developers. Details at gesturepak.com. In this episode, Scott talks with Mark Powell, senior software engineer at Jet Propulsion Laboratories, about his work on the Mars lander missions, including the most recent, Curiosity.
Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and today on the line we've got Mark Powell. He's a senior software engineer at Jet Propulsion Laboratory, if that's not a pretty scary-sounding company. What is Jet Propulsion Laboratory, and how does that relate to space?
Yeah, Jet Propulsion Laboratory started out in the 40s during the World War II era. The Caltech had a bunch of people who were experimenting with rockets, and with an aim to be able to send observational satellites and the like into space. And so they went out to the Arroyo Seco out here near Pasadena or La Cañada, California, Southern California, and started firing off rockets and eventually succeeded in beating several other institutions in creating unmanned probes to send into space. And that was kind of the start of it. And that was followed up by, a series of missions to the Moon and Mars and Venus and elsewhere, and Voyagers, and things like Viking Lander in the 70s went to Mars and gave us our really first clear pictures from the surface. And here we are today with a couple of rovers on Mars.
And you're a software engineer. How is that different, like, from a rocket scientist? If you're like at a party and someone hears you work at JPL, do you get to say, I'm a rocket scientist?
I guess we can, though I suppose it's not entirely fair. We get to take a lot of the credit for people who work directly on the systems for things like precision landing. And so a lot of us have enjoyed seeing the videos about the 7 minutes of terror about we're going to hit the atmosphere, and then there's all this heat, and then there's parachutes and thrusters and radar and all these elements that come together in perfect synchronicity to guide this spacecraft down to the surface of Mars. There's really just a relatively small team of people who work on that, and then other of us who work on various aspects of the rover itself and the software that is used to plan for it and give it its instructions.
Someone said that a lot of the specs and the hardware for the Mars lander were set a long time ago. So when people who are like me, laymen, see these specs online, they're like, well, this is old. My iPhone has more power than the lander. But why is there such a lag? Is it stability, or what is it that's keeping us from putting the latest and greatest stuff up in Mars?
Yeah, it's totally legacy and totally just due to the age of this project. You have to realize that Mars Science Laboratory began as a project almost 10 years ago. And when it was first spec'd, what it has as far as computing power and the amount of memory and other systems on board were cutting edge at the time. And even now we're only able to make small increments to what was then the cutting edge for systems that have to operate in space. You can't just take like the latest Intel or AMD chips and go wild with it without taking some precautionary measures for operating in an environment where you can have solar radiation hits that will cause your computers to reboot sporadically, randomly. So the compute elements and electronics and instruments all operate under the constraints of operating in what they would call a radiation-hardened environment. The RAD 6000 on Mars exploration rovers and the RAD 750 CPU on Curiosity those are built to handle a radiation-hardened environment. And in fact, all of the kind of CPUs that you have on like GPS satellites and other kinds of satellites around the Earth also have that capability in order to operate in that environment, unlike being safe here on Earth.
You know, initially, as someone who's always kind of working on the latest stuff on the web, when I hear that someone's working on something 10 years old, my first reaction, just as a geek, is I don't want to work on old stuff. But then, this might be a funny parallel. I'm interested in what you think about this. My Xbox updated recently, and it got an all new dashboard and all this new functionality. And I went online, and Xbox is like 8 years old. And they're shoving all of this in like 8 megs of space. And then I said to myself, well, it would be a real challenge to make amazing new functionality on older hardware. And the fact that it's old might mean that I might learn new things about something old and then say, oh, wow, I could exploit this and I can exploit that. So it's a new and interesting challenge, even though the hardware might be older. Is that a reasonable parallel to draw?
I think it's a totally reasonable parallel. It is an interesting challenge to write software for that environment. I have the luxury of writing mostly ground tools, and so I get the pleasure of being able to use things that are more modern, web tools, rich IDEs that run on desktop computers, and that sort of thing. But for those who have to create the onboard software, they have to face that challenge. They have to say, well, sure, I want to be able to create an autonomous driving algorithm that can recognize obstacles and keep the rover safe autonomously, so that we have less people in the loop and we can do more with the time that we have on Mars while the spacecraft is still alive. But they have to do it, on a 200 megahertz CPU with a limited amount of memory, and so they have to be very clever about the approaches that they use to actually implement those algorithms.
How are those decisions made? If you're making ground control systems, you personally, right, work on those systems, is that right?
That's right.
Then what if you say, I want to throw in this open source library, or I want to add this new technique or this new feature? Is that going to take years of specs and documentation? I'm trying to get my sense around, like, I think everyone who's listened has worked at a big company before, and they have that sense of like big company speed versus startup speed. You have a reasonably sized team, but you got a lot of moving parts and you got to get it right. So I want to get a sense of how much bureaucracy is involved in your software choices.
Well, there certainly is bureaucracy involved, as much as there would be anywhere else. As far as open source libraries in ground software, we've been fortunate that we've been able to prove out that using open source libraries for key elements of the work that we do on operating these rovers from the ground can be done at lower cost and can be done at higher quality than just writing all the software ourselves. There are a lot of open source groups that are very good at what they do, and so for one of the significant elements of the ground tools that we use to operate Curiosity, we build it on top of the Eclipse framework. So the Eclipse framework gives us a framework for a rich desktop application that has a lot of things that are given to us that we don't have to write ourselves, and have a community of hundreds of developers who are contributing to that all the time and fixing bugs. And we don't have that many developers here, and so we can build on top of that and really focus on our domain more effectively by making use of the software framework that is available for people to build on top of.
Isn't there a sense of pressure, though? Like, there's that old joke of like, well, this is hard, but it's not rocket science. And I always joke about the difference between writing software in the kind of the real world versus writing software for like medical things or saving babies. If you're working on something that's like a to-do application, like I'm going to go write the world's great new to-do list manager. That's not saving babies from cancer, and that's not putting a lander on Mars. So we tend to be a little fast and loose with our software, with our choices and with our things. We don't all treat the software with the respect that we might want to. Is there this sense of reverence when you're working on this stuff? Like, man, we can't screw this up. We got to write that code slow and steady and test the heck out of it. Or can you be sloppy at all like everyone is?
I think it's much more the former. When you're in the early stages of the project, you have a lot more freedom to experiment and like take the latest and greatest of something and say, okay, I'm just going to prototype this or I'm going to sketch it. With the aim to work with the people who the software is serving and saying, if we give you a tool like this, will you be able to do your job? And will be a more pleasant experience than say this other way of doing things. But as time marches on, at the end of the day, you have to get the job done. And so, it's all about, at this phase, now that we've landed, it's all about, we will test everything before we trust it. Nothing is above reproach. So for the first 30 days of this mission, a lot of our activities have been, pre-scripted with the primary goal of building confidence that all of the tools working in concert actually, operate the way that we designed them to, the way that we intended them to, and that anything unexpected can be investigated, researched, documented, and if anything serious, then find a way to work around it or work differently. So I'd say we're somewhere in between the fast and loose here. Let's build a bright shiny thing that's going to get a lot of attention. Maybe it has a few bugs right now, but that's okay. And the guiding an airplane with people's lives or medical devices or software that runs the International Space Station to keep astronauts alive. It's kind of the other end of that spectrum. And we're guiding a robot on Mars, and so there's not human lives at stake, but nonetheless, a lot of us have a lot invested in this robotic spacecraft, and it's kind of our avatar. And the instruments themselves are also kind of the avatars of the scientists who conceived, proposed them, and built them and put them on the spacecraft. And so, we treat them with utmost reverence and don't, ever want to take any risks that are unwarranted that might jeopardize their safety.
Do you find that there's certain personality types that work best at a place like JPL? I mean, might there be a person that might not be suited for this speed or this tempo or this attention to detail in software?
That's an interesting question.
I guess I'm saying you seem very calm and very measured. I wonder if you might imagine a world where you hired someone. Let's say you hired me, and it seems fine, but then when you bring me into the team, you're just like, hey man, we're putting a robot on Mars, and you're a little bit too much of a loose cannon, Hanselman. We're going to have to ask you to leave. We're all very relaxed here and focused, and you're regularly breaking the build.
No, I think we have, a wide mix of personality types. I think that's fair to say. On the team that I lead for the operation product that we build, we definitely have a good mix. We have, some people who are laid back, and we have some people who are just kind of naturally caffeinated, and different people in between. We have some assertive personalities, and we have some passive personalities. And so, it's up to the team to learn how to work with each other and let everybody play to their strengths, and make sure that no one is minimized. It's overall it's a pretty cool place to work, actually, and we tend to integrate different personalities into the process fairly well, with very few exceptions.
Do you use pair programming? Do you sit together, or do you do a lot of code reviews?
Some of us do. On my team, we do it quite a bit. We find that pair programming is awesome for breaking through blocks. I can sit down and I can code for an entire day trying to figure out this problem, and on my own, and just keep banging my head against it and get nowhere. And then I can, tomorrow I can sit with someone else for 20 minutes and explain it to them, and after 20 minutes, it's like, aha, that's the direction I need to go. I just burned an entire day. That was really costly. So now I've kind of learned my lesson. So there's plenty of times when, you can just go in and fix a bug, on your own if you know exactly what's going on. But if you're building something new, if there's something that's particularly challenging, then pair programming can be really advantageous. And we also like to use it because it kind of spreads the wealth, spreads the knowledge. We're in the fortunate position of being able to work with many aspects of operations, from being able to build 3D visualizations to show where we are on Mars and where's the rover and what's it going to do, to planning out the timing and the constraints and, deconflicting violations of, resources like, oh, you can't use this instrument in this other system at the same time, or there's just not enough power to do that today, all the way down to, let's write essentially the script that the spacecraft is going to execute today and then beam that up to the spacecraft. So there's a lot of interesting problems in a variety of these, this broad domain, which is spacecraft operations. And so we don't want anybody to ever feel like they're like pigeonholed in one area.
Mm-hmm.
And so we just let, people team up in different areas to make sure that nothing ever gets old.
Can you talk a little bit about the difference between the work that you've done for the last several years versus what's happening now that it's actually on the planet? Because I'm sure that the things have shifted now that it's landed. You're not, I assume you're not writing the software for a lander in another 10 years. I mean, some code is stable, but now you're sending programs up to it on a daily basis.
Yeah. So, the system is very stable now. And a lot of the focus has shifted to kind of streamlining the operations of the spacecraft. Like, okay, we have these capable systems and we're building trust in them and we understand, what they can do and what they can't do. But we're all living on Mars time right now. And the whole process of building the script that a rover will execute the next day takes about 16 hours. We want to cut that down as soon as possible. Because what that will allow us to do is that will allow us to shift to a more Earth time schedule, where we can, get up and work like, 9 to 6 type of hours, a few months from now versus the always changing kinds of hours that we're putting in right now.
What does it mean, Mars time? What's the number of hours on Mars? It's more than just being in a different time zone.
Oh, it's very much more than being in a different time zone because different time zones on the Earth are fixed. Because the thing about working on Mars, working in this kind of semi-teleoperated, semi-autonomous mission is that the Mars day is very close to the Earth day, but just different enough to make it a huge pain in the neck for people on Earth to actually try to work on Mars, so to speak. The second on Mars is just a little bit longer than the second on Earth. You have a day that's about 24 hours plus 39 and a half minutes. And so what that boils down to is that a second on Mars is 300ths of a second approximately longer than an Earth second. And so that has the effect of we want to start our planning at night when the rover is finished and have it ready for it in the morning when it's ready to wake up and do something else. We mainly want to operate during daylight hours for obvious reasons, like we want to have sun so that we can take pictures with enough ambient illumination. We don't want to take pictures in the dark and that sort of thing. So, but what that means is that you're getting up and coming into work if you're working every day about 40 minutes later every day. And so when we landed, we started at midnight. We're like, oh, all right, this is cool. We're programmers. We're used to being up late and going to bed late in the morning and, kind of living the nightlife. But, that only lasted a week. Pretty soon we were coming in at 4 a.m. Then we were coming in at 8 a.m. And we were like, oh my gosh, this is not so good. And so it's been about 30 days now. We've rotated almost completely around. Mm-hmm. We're going to have to do it 2 more times by the time we get to 90 days. And then if we're successful, after that third time, we will have learned enough about how to make our operations process more efficient, mm-hmm. And kind of patch our tools and add new capabilities to help us with that, so that we don't have to do it a 4th time. That would be really great for the people who are working here. It's very exciting working on Mars, but after three times of that, I went through it on Spirit and Opportunity, going through it again now. It can be tough for the home life, especially if you have family at home, children who want to see mommy or daddy, mm-hmm. and they don't get to see them as often as they did before. So, want to make the most of our time on Mars. We want to be able to sustain that for a long period of time because we have a mission, a nominal mission for Curiosity that's about 2 years, with expectation of hopefully even more than that afterward.
Wow. So if you've got a 24-hour and 40 minutes or 39 minutes long day. And are you referring to time? Are you saying it's 9 o'clock on Mars? And do you have a watch that's set to Mars time?
Yeah, a lot of us have different ways of coping with that. A lot of the planning and scheduling during the day does happen and is announced during Mars time. So we have like 24-hour clocks that are digital clocks that are wired to Mars time. Some people have watches. Some people have, apps for their iPhone or Android that have Mars time. There's one of our rover drivers is also an Android developer and created a Mars time app for himself. And some people created alarm clocks that are on Mars time. They hacked into a digital alarm clock so they can set their alarm on Mars time and get up for their shift at the right time every day. And there's a watchmaker here in town who, for a couple $100, will adjust a watch for you to make the crystal workings of it, just a little bit slower, so that it'll give you, Mars time on your wrist if you want to wear it.
Mm-hmm.
But relatively few of us indulge in that.
But it hasn't been formalized, though. You haven't sat down as a group and decided what do you call that extra 39 and a half minutes? Is that midnight, or is that just an extra long? Is midnight 100 minutes long? Is that hour between 11 and midnight 100 minutes long instead of 60?
So no, the minutes and the hours and the days all work the same. There's 24 hours and 60 minutes, 60 seconds a minute, and all of that. It's just that the seconds are longer.
Seconds are longer.
And so, so you have to algorithmically map what Mars time is to what Earth time is.
Oh, wow.
And so, yeah.
I see. I tried to, in my mind, I tried to map it like it was a time zone, and you just kind of reminded me that, wait a second, no, if we are taking this longer time and dividing by 24, everything changes. Minutes are slightly longer, seconds are slightly longer. So it could be 11 o'clock, but it's a stretchy 11 o'clock.
That's right. We keep it all, based on what was originally the Babylonians, right? We have 60-second minutes, 60-minute hours, and 24-hour days, but they are in fact actually just a little bit longer. But we kind of ignore that when we're working on Mars, because we want the time systems to make sense intuitively for what people expect. It's like, okay, in 2 Mars hours from now, we're going to have this thing, and so we have Gantt charts and schedules that have meetings laid out. Okay, we're going to start at this time, local mean solar time, and it's going to be 2 hours long, and thus and so.
And I know, as someone who's worked in international banking myself, that time zone math is the number one most painful thing that there is to deal with. And once you add in things like leap seconds, everything goes to heck. How are you managing that? I know that one of the things we do on Earth is we focus on GMT, right? Do everything in Zulu time and adjust from there. What is the clock on the actual rover set to versus maybe your web servers running some software that you wrote?
Right. So there's many different time systems in place. There's the Earth time system, and there's also kind of a nominal Mars time system that has time zones and the whole thing. So they've defined 24 time zones on Mars, and so Curiosity is in one of them, and we use local mean solar time to compute times that happen, on the average in that time zone. And then there's local true solar time that is accurate to exactly where the rover is, that's useful for some other calculations, like computing or simulating how much heat the spacecraft is going to experience on any given day. And then the spacecraft clock itself is just a computer clock on a chip. And it has drift, and we have to model that and work with that. And so there's lookup tables and software that will convert. Okay, how many spacecraft clock seconds was this image taken, for example, and what is that in local mean solar time? What is that in local true solar time? What is that in GMT? And so we have a whole software framework developed at JPL called SPICE that helps us with that. It's used on many different missions to Mars and elsewhere to handle all these time conversions for us. Mm-hmm. And so we kind of rely on that to algorithmically convert between all these time systems that we need to run.
And this might be a foolish question or a wrong question, but how do you know you're right? Like, you're not there. How do you know that this is really how it works? I mean, it's all PhDs with math on paper who are pretty sure things work this way.
Well, there's a number of ways we can kind of check ourselves. One of them is to observe the sun, for example. If our spice routines tell us that at a certain time we expect, Mars to be at this position and rotated around its axis by this much, and the sun to be at this relative location, then we can put the camera up and take a picture of the sun and look at where was the rover and what was its heading and what was the pointing vector of the camera at the sun at that time, and say, yeah, okay, we're doing fine. We know where the sun is. We know when it was there.
Do you do that often? I mean, do you have to check your work? And is there anything that you discovered once you got there? You're like, oh wow, we totally got that wrong, and now we have to adjust for it after the fact. Now that it's landed,
we do check it a lot. We have been fortunate that we haven't found any significant errors yet in the time systems. But as I was saying before, the spacecraft clock itself does have drift, and so eventually it's going to tend to start to lag or start to move forward from where it has been before, and so we have to continually watch it to compensate for that, and kind of adjust the lookup tables that we're using to convert from spacecraft time to the standardized time systems.
And how that drift is being adjusted, how differently from how it might be adjusted on my PC that I'm sitting at looking right now? Like, I have a time server, so I don't have to worry about that, right? I have NTP, and I can let the atomic clock in Colorado figure this stuff out for me. And you are effectively your own atomic clock up there, aren't you?
Well, it's definitely wouldn't call it an atomic clock. I mean, it's just a crystal on a chip, right? So,
but the point is, you're saying, when you say drift, you're saying there's a flaw here that is not a flaw as yet, but there's a characteristic of this that we know to be unreliable. Be the right word, or is it reliably unreliable?
Well, I mean, there's errors in everything, and your crystal on a chip is only going to oscillate, so many times per second in an ideal sense, for so long before whatever error is inherent in that process starts to accumulate. And, it may take 200 days, it may take 2,000 days, but eventually it's going to add a second or subtract a second or whatever it's going to do, because nothing is perfect. So we just, we watch for things like that and adjust for them as we notice them.
One of the things that we who in the software industry on Earth have been watching with a lot of excitement is this openness. People seem to be consistently surprised with everyone's use of open source and their interest in open sourcing stuff. Why are there so few secrets?
Why are there so few secrets? I wish there were fewer secrets. We really like incorporating open source libraries and systems into our systems for a number of reasons, like I was saying earlier. One is that for specific domains that are kind of the same, whether you're working in space or working in a bank or anywhere else, there are some systems out in open source for building frameworks for just getting computing done that are terrific, and would cost a lot for us to duplicate. And so it makes one have to question, well, why are taxpayers paying us to duplicate systems that are terrific that already exist? And so we ask ourselves those questions and say, well, hey, we can do a better job for this mission for NASA by learning and using and vetting this particular open source library to do this aspect of our work, and allowing ourselves to spend more time on learning how to operate the spacecraft better or improve these features that are going to make things more efficient. And part of working in the aerospace domain in the United States is dealing with the legal rules that we operate under. In this country, we have ITAR, which is a set of federal laws that limits what information can be freely distributed pertaining to articles of war and, as it happens, spacecraft that are flown to space or other planets or moons also fall into that category. And so there's actually a lot of information that we are legally bound to keep in-house. And then there's also obviously proprietary information, like at any institution, to maintain a competitive advantage. You want to have proprietary information be protected and remain in-house. But wherever possible, if it's information, for example, like that has come back from the spacecraft on Mars, and it's not per se proprietary, it's not, it's something that was the end result of operating a spacecraft on Mars, but it wasn't the operation of the spacecraft on Mars. It's like a picture that was taken or the location of the rover today. Mm-hmm. There's no reason not to share that information with everyone who has a stake in this, which are all the taxpayers who pay for it.
Very cool. Well, we appreciate it. I mean, just the fact that I'm even able to talk to you is pretty awesome, frankly.
Cool. Thanks. Yeah, it's always a treat for us to be able to talk to people about what we do. We're very excited about it.
Cool. Well, thanks a lot. That's Mark Powell from the Jet Propulsion Laboratories and working on the ground software, operating Curiosity on Mars right now. This has been another episode of Hansel Minutes. We'll see you again next week.